Ask any AI chatbot a very simple question. How many letter R's are in the word strawberry? For a long time, the smartest models on the planet got this wrong. The same system that can write working code, debug a database, and explain quantum mechanics could not count to 3, and the reason is on the screen right now, because to the model, strawberry is not a word made of 10 letters. It is this: 3 lumps, straw, burr, rye, and you cannot count the letters inside a lump. Stick with me for the next 15 minutes, because once you see why 4 different confusing AI behaviors stop being confusing all at once. Let me show you the 4. Symptom 1, the berry, it miscounts letters in a word a 5-year-old can spell. Symptom 2, the math, it fumbles arithmetic that a pocket calculator solved in 1970, not complicated maths. Addition. Symptom 3, the toll booth, and this one is the one almost nobody talks about. Write the exact same sentence in Hindi instead of English, and it costs you 2 to 3 times more money. Same meaning, same information, higher bill. Symptom 4, the glitch. A few years ago, there were certain strange strings of characters that would make these models produce complete nonsense. Random words, insults, scripture, and for a while, nobody could explain it. 4 symptoms that look completely unrelated. They are not unrelated. They share one single cause, and that cause happens before the AI does any thinking at all. Here is the thing nobody tells you when you start using these tools. The model never sees letters. Not one, not ever. On the left is your side, the human domain. To you, language is a flowing stream of meaning. Letters and words are fluid. You can zoom in on a single character whenever you want. On the right is the machine domain, and it does not receive a stream, it receives a line of discrete lumps. Tok, ni, za, tyon. Between the two, there is a barrier, and that barrier is called tokenization. Now here's the detail that matters most, and it is written along the bottom. The tokenizer is not part of the neural network. It is a completely separate piece of machinery, built separately, trained separately, on a different pile of text at a different time. It runs before the model wakes up. So hold on to this sentence, because everything else in this video hangs off it. A token is not a word, and it is not a letter. It is a frequency-shaped lump invented by a counting machine before the model ever learned to think. So why chop text into lumps at all? Why not something sensible? There are 3 options, and 2 of them are disasters. Option 1, raw characters, 1 brick per letter. The simplest possible idea, look at the attention costs, brutally high, because attention cost scales roughly with the square of the length. So a single page becomes thousands of pieces, and every piece has to be weighed against every other piece. The vocabulary is tiny, only about 256, but the semantic value is basically 0. A single letter on its own means nothing. Option 2, whole words, 1 brick per word. Now the attention cost is lovely and low, and the meaning per piece is high, but look at the vocabulary, infinite, and permanently incomplete, because new words appear every single day. Brand names, slang, typos, scientific terms. The moment somebody writes a word that is not in your list, the model has nothing to work with. Blank. So the answer is option 3, subword tokens. The Goldilocks, compromise. Common words become 1 efficient brick. Rare words shatter into fragments. The vocabulary is bounded somewhere between 50,000 and 200,000 entries. And critically, nothing is ever truly unknown, because underneath everything, the system can always fall back to raw bytes. Remember that fallback. It comes back at the end of this video. Now, my favorite part, how the bricks are actually made, because nobody sat down and decided what a token should be. Counting decided. The process is called byte pair encoding, BPE, and it works like a factory. Step 1, you pour in an enormous pile of text, billions of words, and at the very start, every single byte is its own tiny token. Those are the little cubes at the bottom left. Step 2, you scan that entire pile and ask one question. Which 2 pieces sit next to each other most often? Maybe it is T and H, because the and that and this are absolutely everywhere. Step 3, you glue them. TH becomes 1 new, larger brick. Watch the arm on the screen. T and H go in. Thete comes out, then T and E, and now you have the step 4. Repeat. somewhere between 50,000 and 200,000 times. And what rolls off the conveyor belt at the end is exactly what you see. Water equals one clean brick each because they appear constantly. And down the end, the small ones, fragment, because those pieces did not appear often enough to earn a promotion. That is the whole secret. The size of a token has nothing to do with how important the word is. It only reflects how often it appeared in the pile. Two consequences fall out of that, and both surprise people. Point one, white space gets absorbed. Look at these two bricks. On the left, cat with no space. On the right, cat with a space in front of it. These are not the same token. They are not variations of each other. They are two completely different entries in the vocabulary with two completely different identity numbers, 3,241 and 981, which means the spaces and line breaks in your prompt are not invisible formatting. They are real pieces of input, and that is one honest reason why reformatting a prompt sometimes changes the answer far more than it feels like it should. Point two, and I love this one, byte pair encoding was not invented for artificial intelligence. It was invented in 1994 by a man named Philip Gage as a way to compress computer files, to make them smaller. Find the most common pair of bytes, replace it with a shortcut, repeat. A zip file trick from the 90s is sitting underneath the foundation of modern machine reasoning. It was never designed for meaning. It was designed for storage. And we are still living with that decision. Right? So we have bricks. Where does actual understanding come in? Follow the pipeline left to right. You type the cat. That is the input. It gets fractured into token chunks, the and space cat. Then each chunk gets stamped with an integer. 464, 3,797, and that is the complete output of the tokenizer. Text goes in, a list of integers comes out. No meaning, none at all, just index numbers, meaning arrives at the next stage. That wall of drawers on the right, that is the embedding matrix. There is one drawer for every token in the vocabulary, and inside each drawer is a learned bundle of numbers representing everything the model has figured out about that exact lump. Is it warm? Is it a living thing? Does it usually start a sentence? The integer is just the drawer number. It opens the drawer. The contents are what the model actually thinks with. And notice the split. The drawers were learned slowly from enormous amounts of reading, but the labels on the front of them, the tokens themselves, were decided years earlier by a counting algorithm that understood nothing. Two different systems bolted together. Keep that seam in mind. Keep. Now, how does it actually write? It plays one game over and over and over. Step one, score. It looks at everything so far and produces a score for every single token in the entire vocabulary, all 100,000 of them. How likely is each one to come next? Step two, pick. Those scores go through a filter called softmax, which turns them into probabilities. Thousands enter, one exits, usually a high scoring one, sometimes a surprising one, which is precisely why these models are not boring. Step three, append. That one token gets stuck onto the end of the line. Step four, restart. And this is the part people find genuinely strange. It reads the entire thing again from the beginning, including the piece it just wrote, and asks the same question. What comes next? Let that land for a second. Every sentence an AI has ever written was built this way. One piece, then start over. One piece, then start over. It has no plan for the end of the sentence when it writes the beginning. And there is a practical note in the corner worth reading out loud. Reading your prompt happens in parallel, so it is fast. Writing the replies sequential, so it is slow. That is why the first word takes a beat, and then the rest streams at you. It is also why API pricing is strictly per token, and why context windows are measured in tokens, not words. A 200,000 token limit is not 200,000 words. So now let's go back to those four mysteries. All four on one screen, and read the line under the title because it is the honest summary of this entire video. The model is not failing to reason. It is operating perfectly on badly chopped materials handed to it by a blind pre-processing step. Symptom 1. Strawberry. The flaw is opaque lumps. Straw and berry are two shapes. There are no letters inside them to count. Asking the model to count the R's is like asking someone to count the R's in a potato. And a fair update here because I want to be accurate. Many newer reasoning models do get this right today, but not because the blindness went away. They learned a workaround. They spell the word out first. piece by piece and then count. The underlying problem is completely unchanged. Symptom 2, arithmetic. The flaw is scrambled place values. The number 1, 2, 3, 4 might be chopped into 12 and 34, or into 1 and 234, depending on the tokenizer. Place value is destroyed before the model even begins. That is a terrible foundation for maths, and this is exactly why some newer tokenizers now force numbers to split digit by digit deliberately, and arithmetic gets measurably better when they do. Symptom 3, the language tax. The flaw is lopsided training frequency. I am giving that one its own slide next because it deserves it. Symptom 4, glitch tokens. The flaw is empty drawers. Remember that seam I mentioned. The tokenizer and the model are trained separately, so it is entirely possible to end up with a token that exists in the vocabulary that the model itself almost never encountered while learning. A labeled drawer that is empty. The famous case is a Reddit username, solid gold Magacarp. This person posted the same handle over 100,000 times in counting forums. The counting machine saw it everywhere and gave it its very own dedicated token. But when the model sat down to actually learn, those posts were barely in its reading material. So the drawer had a label on the front and nothing inside. And when anyone typed that word, the model would open the drawer and produce anything at all except the word you asked for. Unrelated words, insults, religious texts. These are called glitch tokens or undertrained tokens, and they are not just a curiosity. Researchers have shown they can sometimes be used to slip past content filters, and there are now automated methods for hunting them down inside a vocabulary. That specific one got fixed. Newer tokenizers just split that name into 5 ordinary pieces, but the seam that caused it, the gap between the counting machine and the learning machine, that is structural. This is the section I most want you to remember. Remember that the bricks were built by counting a pile of text, and that pile was overwhelmingly English, so look at the top conveyor. English got beautiful, large, efficient bricks, frequently one whole word per brick. Now look at the bottom conveyor. Same sentence, same meaning, same information, but in Tamil or Hindi or Amharic, it arrives as fragments, byte-level scraps, and on the right-hand end, the price tags. Because you pay per token, and your context window is counted in tokens, this means users writing in underrepresented scripts pay roughly 2 to 3 times more for the identical message. They fit less into the same conversation, and they often get worse quality on top of it. Researchers have documented this carefully, and the genuinely uncomfortable finding is that this tax falls hardest on regions where these tools were already the least affordable. Nobody sat in a room and designed that. It is not malice, it is arithmetic. It is what happens when a counting machine counts a lopsided pile, and then that count gets frozen into the foundation of a product used by the entire world. So if tokenization causes all of this, why do we still do it? Look at the top half, the current standard, a rigid, fixed dictionary. And notice the problem it creates. This is a sentence gets carved into the same size pieces as a chunk of code. Compute gets wasted on the easy parts, and there is not enough attention left for the hard parts. Raw bytes were always the obvious alternative. But a sentence that is 200 tokens is roughly 1,000 bytes, 5 times longer. And attention scales badly with length. It was simply unaffordable. Look at the bottom half. In December 2024, Meta AI introduced the byte latent transformer, BLT. Instead of a fixed dictionary, it takes raw bytes and decides on the fly where to draw the boundaries. And it decides based on surprise. There is a small entropy model watching the stream. Look at the blue region. This is a sentence. Boring, predictable. So it gets scooped up in one big lazy handful. Now look at the pink region. Messy code with a typo in it. Suddenly it fractures into tiny pieces, and the model examines it almost byte by byte. Compute gets spent only where the data is actually difficult. And the results are genuinely striking. An 8 billion parameter version matched a comparable tokenizer-based model at similar compute while handling typos, code, and low resource languages far more gracefully. Now let me be honest with you, because a lot of AI content is not. Read the status box. Conventional byte pair encoding still wins on small training budgets. This needs architectural changes, so you cannot drop it into an existing system. And essentially every model you personally use today still has a tokenizer inside it. This is not shipped, it is a direction. But look at how the question has changed. For years, the research question was, which merge order is best? Now the question is, should the model see tokens at all? Right. 4 things you can do the moment this video ends. 1, Go and look at your own text. There are free tokenizer viewers online or 3 lines of Python with TikTok in. Paste in a prompt you actually use and watch it fracture. Honestly, this is the moment it clicks. If you only do one thing from this video, do this one. 2. Estimate your limits in characters, not words. English prose averages roughly 4 characters per token. Code costs more because of all the punctuation and indentation. Non-Latin scripts cost considerably more. Stop counting words. 3. Stop asking for character level operations, counting letters, reversing strings, strict syllable counts. Either expect it to fail or explicitly ask the model to spell the word out with dashes first and then do the task. That single instruction fixes most of these failures, and now you know exactly why it works. 4. Watch your white space. Leading spaces and stray line breaks are real, distinct tokens. Keep your formatting tight and consistent, and the one sentence to walk away with. A token is not a word, and it is not a letter. It is a frequency-shaped lump invented by a counting machine before the model ever learned to think, and almost every strange thing an AI does traces right back to those lumps. If that made something click for you, that is the entire point of this channel. Subscribe and tell me in the comments which of the 4 surprised you most. I will see you in the next one.